So when we're looking at expanded octets, now we have 5 and 6 groups around the central atom. Then we have to incorporate the d orbitals. And the first energy levels that you have d orbitals that you can incorporate is energy level 3. So that's why we see expanded octets from the third period and down. So for sp3d hybridization, what we have is we have 5 electron groups that make a trigonal bipyramidal electron geometry. The orientation of the orbitals are these sort of, I don't know, bronze-colored ones on the inside. They give the 120-degree angle this way around the equatorial part and 90 degrees top and bottom. So for this compound, which is ASF5 over here, what we have is we have a bonding scheme that says this is a sigma bond between an arsenic sp3d orbital and a fluorine p orbital that's out here. Closer look at the bonding scheme. Arsenic has 5 valence electrons, so it looks like this, and its ground state. Once we hybridize it, what we do is we put the electrons all together into the hybrid orbitals like this. These are the unhybridized d orbitals at the top. So when I look at the orbital diagram for fluorine, fluorine looks like this. This is 2s and 2p. We have 7 valence electrons like this, and there's 1 unpaired electron. So what's going to happen when this bond forms is a sigma bond will form, because remember these hybrid orbitals only make sigma bonds, between the 2p unhybridized orbital on fluorine and the hybrid sp3d orbital on the arsenic. So the description would be sigma bond between the arsenic sp3d orbital and the fluorine 2p orbital, like that. So adding one more electron group on the central atom would make it sp3d2 for a total of 6 groups on the central atom. The bond angles are all 90 degrees in that. So for sulfur hexafluoride that we show here, what we have is a sulfur in the middle, right, with its sp3d2 orbital and the fluorine with its p orbital. If we look at the orbital diagrams, sulfur has 6 valence electrons, so we go 1, 2, 3, 4, 5, 6, like that. When we hybridize and get the 6 sp3d2 orbitals, we can space the electrons like this. So that's all 6 electrons. The fluorine, again, is 2s and 2p. And again, it has 1 unhybridized orbital that it can bond with. So overall, we end up with the description of the bond as being a sigma bond, because it's head-to-head, of an sp3d2 with a fluorine p orbital. So we can summarize the hybridization schemes like this table for the different electron geometry. Right? If it's sp hybridized, it's linear. Bond angles are 180 degrees. If it's 3 groups, it's trigonal planar, would be sp2. That's 120 degrees. And for 4 groups, you end up with sp3, and the angle between the hybrid orbitals is 109.5 degrees. And then we come to the expanded octets, right, where we get an sp3, and I don't know what happened to that d or that d there, but it should be big. D, you end up with 2 bond angles. The hybrid orbitals create a 90-degree angle to the equatorial, and then also 120 degrees around the axis of the equator. And then for 6 groups, you end up with sp3d2 for a total of 6 orbitals, and 6 hybrid orbitals are generated, and the bond angle between all the orbitals is 90 degrees. Now, Vesper theory does have some advantages over Lewis theory. And one is it predicts the properties. It predicts how the electrons bond. It predicts relative bond strengths and bond lengths. It predicts sort of the rigidity of bonds. And it also helps to give us ideas about what the bond angles are and why the bond angles exist in different atoms. But still, there are some weaknesses. One of the weaknesses would be that we never really touched on how resonance is accounted for in valence bond theory, and it doesn't actually do a very good job of doing resonance. And there's still, it isn't able to predict, like Lewis theory isn't able to predict, the magnetic properties of molecules. So atomic, orbital theory, I should say, quantum mechanics orbital theory, is good at predicting magnetic properties, but valence bond theory doesn't quite do that very well. And in essence, because every bond results from pairings of electrons, all molecules should be, in this theory, diamagnetic, because all the electrons get paired up. It says here magnetic behavior of O2 because it turns out if you look at oxygen, oxygen can actually stick to a magnet. So liquid oxygen, when it's poured over a magnet, actually is attracted and sticks to the magnet. And again, valence bond theory doesn't do a very good job of explaining that. So then what has to happen is we have to move on and expand and look at another theory called molecular orbital theory.